Hello and welcome back to Mr. Saucedo's YouTube videos. Today we're actually going to be going back to chapter 15. So this is kind of odd to say, but in Zumdahl, the 7th edition, the end of chapter 15 is about solubility equilibrium. But in reality, most of the time people think of it as chapter 16 because it was in, I think, probably the 8th edition that he split it up into two sections. So technically you're going to see it say chapter 16, and that is true of the current version of the textbook, including the 10th edition. But in reality, in the 7th edition, it's actually at the very end of chapter 15. Okay, so first things first, let's talk about solubility equilibria and the solubility product. So there's one type of thing that we have not discussed yet, and that would be the solubility product. So we've talked a lot about equilibrium and a lot about K value, right? So there's another form of a K value called a Ksp. And so the Ksp is the solubility product, and it is basically an equilibrium constant for a given solid dissolving in a liquid like water at a given temperature. And so the thing that you need to know about it, right, is that the more soluble, right, something is, the higher the Ksp value is. The less soluble, the lower the Ksp value is. So in reality, when we talked about solubility rules and we talked about what dissolves and why and all of that stuff, technically everything has some Ksp value. So that means that in reality, what makes something that is super insoluble like lead to iodide from something that is really soluble like sodium chloride, what separates those two from each other is the Ksp value. If the Ksp value is super low, the amount that is dissolving is super low. On the other hand, if the Ksp value is very high, the amount that's dissolving is very, very high. So I like to think of it like this. Technically, everything has a Ksp value. And so technically, even you are slightly soluble in water. So a good example of that would be right here. We have Bi2S3 as a solid. And so when it dissociates into these bismuth ions and these sulfide ions. And notice, right, that we have 2 and 3. So we still have to maintain the law of conservation by putting coefficients in front of everything, right? So even though I don't probably need to tell you that, it's still true. How would we write the Ksp for this? Well, remember the Ksp, or the K value, I guess I should say, right? The equilibrium for something is the products over the reactants, and we only include aqueous and gaseous substances. So in the case of something dissolving, we only include the ions that it's breaking apart into. And just like before, we still take whatever the coefficient is and we raise it to that power. So in other words, this would be, whatever that concentration is of bismuth squared, and whatever the, concentration of sulfide is cubed. Okay, and we multiply them together to get the Ksp value. So let's check this out, right? We've got, in comparing several salts at a given temperature, does a higher Ksp value always mean a higher solubility? If yes, explain and verify. If no, provide a counterexample. Okay, so based on what I told you on the previous slide, a lot of people would say the answer to this is yes. But the answer is no. And the reason why the answer is no is that in order to talk about a Ksp value of something, the salts that you are comparing must contain the same number of ions. So in other words, because we are squaring and we are cubing things, right, in order to have a really good discussion where we're comparing two salts to each other, the only way to do that directly would be to have the exact same number of ions that something is breaking up into. So in other words, right, if I have something that dissociates like silver chloride, right, that's one silver cation and that's one chloride anion. And I were comparing it to something like barium chloride, right? Barium chloride is one barium and two chlorides. That would be not a very fair comparison because we're going to end up with different numbers no matter what anyway. Also, barium chloride is super soluble in water, and silver chloride not so much. So maybe that wasn't the best counterexample, but still, you get the idea. Now, let's actually do something with this then. Calculate the solubility of silver chloride in water. And I literally just used it as an example, so perfect. Here's the Ksp value for silver chloride. So notice that it is a very, very, very small number. Okay, remember, the greater the Ksp, the more soluble something is. This is not very soluble. So what do? Well, you need to know what our balanced equation is going to be. And so we have one silver ion and we have one chloride ion. Perfect. So the Ksp is this. So, right? So this is my Ksp, and it's going to be equal to the product of these two multiplied together. So all I've got to do is set that equal to x, right? That's going to be my unknown. So if I have x times x, that's x squared. So now by taking the square root of both sides, I now have my solubility. So 1.3 times 10 to the negative 5 moles per liter of Ag, and exact same amount of Cl. And yes, that makes sense, right? If I multiply those two together, if I multiply this by itself, I end up getting this number. Okay, so let's do a different example. What about the solubility of silver phosphate? Okay, so silver phosphate, think through what that formula would be. It's Ag3PO4, right? And notice that the Ksp is way, way lower for silver phosphate. Silver phosphate is much less soluble in water, even more so, right, than silver chloride. So I have 3 silvers, I have 1 phosphate. So how does that work? Well, same exact thing, except I have to cube the quantity of Ag that I have, and I have to not do anything to the PO4 minus, to my phosphate. But that's the Ksp value, so that still goes here, and it's equal to the product of both of these together. Now, a lot of times people say, okay, great. So it's x cubed times x, that's x to the 4th. All right, now, a lot of times people get confused by this and they think that it's double dipping. It is not. Keep in mind that I'm always going to have 3 times the amount of Ag as I do PO4, right? That just kind of logically makes sense. There's a 3 here. And so that means no matter what, I'm always going to have 3 times the amount of this compared to this. So when I'm plugging that in, I do need to include the 3 here because it's really 3 times that amount cubed. And again, a lot of times people say, well, you're already cubing it. Why would you need to do this? The cubing bit is taking care of the fact that this is equilibrium, right? So that's just, the equilibrium constant kind of stuff that we talked about before. This is taking care of the fact that the relationship between these two numbers is always going to be 3 times the amount of this. So in reality, when I do that, it ends up being 27x to the 4th power. Okay, so now I need to divide this by 27 and then take the 4th root of everything. And when I do that, I get, well, actually, I guess I should do that one step at a time. When I divide by 27, I get this. And then when I take the 4th root, I end up getting 1.6 times 10 to the negative 5. Now, keep in mind, right, that logically this should make sense, because if that is my x value, if that is what this value is, I would have 3 times that amount of this. So I would multiply that by 3. And then if I were to plug that into this equation, now I would have, the ability to get my 1.8 times 10 to the negative 18. Okay. How does solubility of silver chloride in water compare to that of silver chloride in an acidic solution made by something like nitric acid, if I were to add that instead? Explain. Okay, so what we're really getting at here is the common ion effect, and we already talked about that at the very beginning of chapter 15. So the solubilities should be the same. And why would the solubilities be the same? Because technically something like nitric acid, or any strong acid like HCl or something, is going to completely dissociate in water. So since it's going to completely dissociate, it's not really going to change anything. Now, what if we had a different situation though? So let's say we had silver phosphate in water and we wanted to do the exact same kind of thing. Okay, silver phosphate would be more soluble in an acidic solution. Think through all of the stuff we've talked about in acid-base equilibria so far and see if you can figure out why. I will say pause, if you think that you want to think a little bit more about this problem. So I'll tell you the answer. Phosphate ions, PO43 minus, that technically is a Bronsted-Lowry base. It's also going to be able to react with a strong acid in order to make, something like hydrogen phosphate or dihydrogen phosphate, right? And so that's a good example of Le Chatelier's principle and how Le Chatelier's principle can affect solubility and the solubility product of something. Okay. So in the case of silver chloride, that wasn't a problem because it was totally dissociating, and silver chloride is not going to give you acid base anything. Whereas silver phosphate is actually a very good, well, it's weak, but still it's a base and it can be used in an acid base reaction in that way. Whereas Cl cannot. Cl is, remember, a horribly weak base. It's the most weak base we could get, or one of the most weakly basic things we can get, because it is the conjugate base of a strong acid. Phosphate, not so much. Phosphoric acid and all that stuff, that's very, very weak. And so it's going to be a pretty decent conjugate base. All right, how does the Ksp of silver phosphate in water compare to that of silver phosphate in an acidic solution? Now, you might think, wait, we just said that. Well, actually, you know what? I'm going to go back to the previous slide. Why not? Solubility. Solubility is the X that we were solving for, right? Remember, Ksp is a single number, right? The Ksp value is something you can look up. It never changes. So the Ksp value is not going to change. The solubility could change, but the Ksp value is going to be the same no matter what, if that makes sense, right? And I don't want to have to click all the way back through, but remember that Ksp is a single number at a given temperature for dissolving a particular substance. And so that never changes. I mean, okay, it changes with temperature, but we're assuming that we have the same temperature. So that's not going to change. What can change is the X, that solubility part. That's allowed to change. When we multiply them together, though, right? When we multiply our, silver ion part and our phosphate ion part, though, no matter what, we're going to get Ksp, even if the solubility of silver or phosphate is slightly different. Okay. Now calculate the solubility. All right. So now we're going back to some of the stuff we were looking at before we went over this concept stuff. So calculate the solubility of AgCl in 100 milliliters of 4.00 times 10 to the negative 3 molar calcium chloride. I spot the common ion effect. How would I spot the common ion effect? Well, let's write down the equations. So I'm going to use blue to represent my silver stuff here. So there we go. Calcium chloride, hopefully you remember that calcium chloride would have double the amount of chloride ion. And I see a common ion. I see a Cl minus and I see two Cl minuses. So that immediately lets me know, okay, there's going to be something I'm going to need to do. And that would be, take a look at this. It's telling me the molarity of calcium chloride. I can use that information to inform what my X value is going to be in my solubility product for my Cl. And so how do I do that? Well, remember, I'm going to have double. So if the molarity of calcium chloride is this, the molarity of the chloride portion is going to be double. So double this is 0.008 moles per liter. Okay, great. I can plug that into the Ksp for my silver times my chloride. So remember, Ksp is right here, 1.6 times 10 to the negative 10. Perfect. Ag, don't know. I have no idea what that would be, but I do know what my chloride would be because it's telling me that I'm mixing it in 100 milliliters of this. Also note that the 100 milliliters was useless information. I didn't need to do anything with that. All I needed to know was the concentration, because remember, in Ksp and in any K value, it's just the concentrations that matter. Now keep in mind, I don't have to raise these to any powers because it's 1 Ag and it's 1 Cl. All right, let's do that. We get 2.0 times 10 to the negative 8 moles per liter. That would be my solubility. All right, let's try this. Calculate the solubility of AgCl in 4 times 10 to the negative 3 calcium nitrate. Do you notice that there's no common ion? So let's look at both. Here's my original. This would break apart into a calcium and also 2 nitrates, and there's nothing in common, so I don't need to use this information at all. This is entirely useless information. All I have to do is set it up the same way I did at the very beginning, where I have a certain amount of Ag and a certain amount of Cl. Those are going to be both x's. I take the square root, and I end up with 1.3 times 10 to the negative 5, which is the exact same number that I ended up with when I did this originally. So this only works, or this little process here, can only happen if there are no common ions. If there are common ions, then we can actually utilize that information to plug in a portion of our equilibrium. Okay, now precipitation and qualitative analysis. So mixing two solutions. Now Q represents a solution that is not at equilibrium, right? So we're changing something, and we're going to be comparing that to the Ksp value. So if Q is greater than the Ksp, the solution is supersaturated and it cannot dissolve anymore solid, right? So that would be representative of this kind of curving line here. If Q is equal to Ksp, that means the solution is saturated and it is at equilibrium. So that would be this line right here. Now, if Q is less than the Ksp, that means the solution is unsaturated and so it will dissolve. And so that would represent this line here. So in other words, you can think of it as it will keep dissolving and your solid will keep dissolving until it finally hits this point. Once it hits this point, it is saturated and no more, at that temperature at least, no more solid will dissolve. Now, if you keep adding more, right, now we're doing this. Now we are literally increasing. We are now getting super saturated. So that means we just have like solids stuck to the bottom. And so that's kind of the relationship between Q and Ksp. Now, selective precipitation is not necessarily something that you're going to see on the AP exam. I think it's kind of cool though, right? And so the idea is that, is there something that we can add if you have a mixture of things floating around in solution in order to remove something from that solution, but only to remove one thing? You don't want to remove everything. You just want to remove one ion. And so in that situation, you can choose an anion that will form a precipitate that will only mix with one particular metallic ion that you have in your mixture. And so a good example of that would be, what if we had a mixture of barium and we had a mixture of silver ions? Well, if I added some salt to it, the Ag would precipitate out as silver chloride, but barium chloride is soluble in water, and so I would end up with the barium still in my solution. And this is an excellent way of removing something from a solution. Now, again, it's not really something that you'll see on the AP exam. They used to do something like this on the AP exam, but not anymore. And then same thing with this. So the last section here also doesn't show up on the AP exam anymore, but I will show you something that could show up on the AP exam that kind of involves complex ions. On the bright side, that means you don't have to name any of them because they have horrible, horrible names. But charged species consist of a metal ion surrounded by a ligand. Now, a ligand is a fancy term for a Lewis base, and they can have some pretty cool looking shapes. We end up with very very often some octahedral shapes like this, which is kind of cool. So here we have a cobalt with a 2 charge, a 2 plus charge, and we have 6 water molecules surrounding it. Now you might say, water's the Lewis base? Yeah, right? It's got 2 lone pairs of electrons on our oxygens, according to, the Lewis base theory. Yeah, that's totally acceptable as a Lewis base. Here we have platinum, and it is surrounded by these chloride ions. So we have platinum with a +4. So we have platinum 4. And then we have all these negative Cl's surrounding it. And so, yeah, Cl is also a Lewis base. And so these are both complex ions. All right. And so most of the time when you dissolve a transition metal ion like this, it's going to end up with a complex ion forming. So you're going to end up with some sort of coordination complex. Now, here's the only thing I can think of that involves complex ions that they might ask about on the AP exam. And I think it's a really cool example, though. So on the bright side, you don't have to know anything about complex ions, but these look like horrifying formulas. So I like to say, like, well, I'm going to show you at least some horrible complex formulas first, so that at the very least, you're not surprised if you see something that looks this bad. So we have heat plus this cobalt complex that's surrounded by water, plus 4 Cl minuses. And it's in equilibrium with this cobalt complex that has, 4 Cls and water molecules on the opposite side. And so this is an endothermic reaction because heat is on the left side. So heat is on the reactant side of this. And so what I think is cool about this is they have 2 different colors. So this complex is pink and this complex is blue. So using Le Chatelier's principle, we can actually shift it from pink to blue and back and forth again. So what if I were to add heat? If I add heat, according to Le Chatelier's principle, this is going to move away and it's going to try to make more of what's on the opposite side. So that means that it's going to go from pink to blue, which would be kind of cool to see. What if I put it in ice? Well, then it's going to go the opposite way, right? It's going to say, okay, I'm going to need to generate more heat in order to warm it up. And so it's going to move from the blue side to the pink side. So we would turn it from blue to pink. What if I were to add some NaCl? Well, Cl appears as a common ion on this side, right? So if I were to add more of it, that means that I would shift the equilibrium to the blue side in order to remove, basically in order to counteract the Cl that I'm adding. What if I were to add water? If I were to add water, now I'm applying stress to this side, so that means it would move to the left and it would start to turn pink. And then in the last case, I really like this one. What if I were to add AgNO3? Well, remember, like we just showed in 16.2 on that slide, Ag and Cl, right? So when Cl and Ag mix, we end up creating a wonderfully insoluble salt. And so by doing that, that's going to end up making more of this pink stuff. Why? Because I'm removing Cl. And so if by adding this ion, which is going to form something insoluble, I'm going to be basically extracting Cl from this equilibrium. And that's going to end up making it move towards the left to try to replace it and make more Cl. And that is literally it. So it was a short little section. Like I said, if you have any questions, please let me know. Thank you for liking and subscribing. And there's really only one chapter left on electrochemistry, and we're finished with AP Chem.